So hello, welcome to the session on Service Mesh. We might be in the smallest room, but we filled it, so thank you. My name is Rob Crowley. I'm a principal consultant for Retry. Previous to that, I was the technical lead for APIs and authentication at Bank West. So the vast amount of my career has been designing and building distributed systems. So this is a topic that's very close to my heart. So we're going to start with a bit of a pop quiz. So who has heard of the service mesh pattern? Ooh, this is good. Probably a bit more of a tricky question now. Is anyone running a service mesh in production? Excellent. That's the first time I've seen a hand. Awesome. But that's cool. For the rest of us, that's why we're here. So we're here to learn a little bit more about the pattern. But I don't want you to just come today and get an idea about this was some cool piece of tech, but not really be sure how to apply it to your context. So what we want to do today is have an understanding about why is a service mesh even a thing? What category of problems does it help address? And also then give you the understanding to be able to take it back to your organizations and say, yes, this is something that can help, and in what context. We're then going to contrast service meshes to other patterns or practices that we had over the years, so API gateways and our good old friend, the enterprise service bus. So we're going to see how there's certain similarities between these, but also the differences and sort of the same end goal, but achieved in a different way. Technology is all well and good, but what really excites me is the things that it enables us to do. How does it change the way we can do our work? So what we're going to look at then is how service meshes can give access to a whole host of really advanced capabilities that were previous the remit of tech luminaries like Google alone, but now actually brings a lot of these capabilities within the reach of mere mortals. And most of all, I would love to start a conversation or continue a conversation about service meshes in the Sydney technical community. And realistically, we only have an hour together. So disclaimer, I will not be able to turn every single person in this room into an expert in that time. But if I can inspire you just enough to go and learn more about this when you leave, that would be an amazing outcome for me. So a very smart person once told me that every good presentation should have a story. And so this presentation has a story too, and it's a love story. It's a love story of when Service A met Service B. And this is back in the 1950s. These are baby boomer services, and they're both deployed on the same host, and they talk every day. And because they're on the same machine, it's amazing this conversation's happening. It's very reliable. They're having an absolute wonderful time. But good things never last, do they? As part of a digital transformation, Service B is rehosted. Suddenly, all of these conversations that they could have before, it's now cross-process. They're on different machines. How will this love story end, you ask? But that's okay. Distributed computing is easy, isn't it? It's not going to be that hard. You know, this will be okay. No. Long-distance relationships are tough. So first of all, before, Service A could just call Service B and get a response instantly. Now suddenly it's having to write these love letters, and it sends them in the post and it doesn't get a reply. Then what do? Do you seem needy? Do you just keep sending the letters? No, we're not. We're going to hold back a bit, aren't we? You know, they'll definitely reply at some point. But there's suddenly all this doubt, right? And at the same time, because these are now two separate systems, the ability for A to pen his love letters and send them across is completely divorced from the ability of the other service to consume it. So again, we could have this amount of traffic downstream without the other service being able to consume it. And then packet loss happens, potential degradation of your services as well. So all this reliable ability that we took for granted when we were running in process suddenly evaporates. And back in the 1990s, Peter Dutch and a number of his collaborators at Sun highlighted exactly some of these problems, and he named them the 8 fallacies of distributed computing. And by naming them as fallacies, it makes us take account of them. So these are things such as the network is not reliable. So the network, we assume that it is when we're running in process, but it's not. So we have to take account for that. latency is not zero, there's a delay. Speed of light 300,000 kilometers per second, but that's not instant. That's still 50 milliseconds latency between Perth, where I work and live, and Sydney. And that's even on an excellent network. If you take into account all the other hops and routers, then that's get delayed again. So we have all these other problems that we didn't have to face in these more basic computing models. And let's see what actually happened. So what I previously alluded to was flow control. So in flow control is the ability for one service to detect the amount of traffic that it's sending downstream, and then modify the amount it sends such that it doesn't overload the downstream service. And again, we're back in the 1950s. So, back at this time when computers were relatively rare, it was the application developers ourselves that would have had to solve this problem. So within the business logic of my service, I would suddenly have to account for, did the message ever arrive? Do I now have to buffer it to then send downstream again? What if I send it twice? What if I send it out of order? All of this reliable delivery concern, again, was part of the services themselves. And even with this one flow control example, we're suddenly kind of thinking, oh my goodness, this relationship is doomed. Woof. This distributed computing thing is just a little bit harder than we might have initially suspected. But there's more. So again, in three broad categories of reliability, observability, and traffic management, these are just umbrella terms that they in themselves hold a huge amount of nuances. So with traffic management, we have load balancing. How do I distribute my traffic across all of the nodes in my availability pool? But maybe that's not good enough. Maybe you need to have latency-aware load balancing such that you can route your traffic to the node who can best respond in a timely fashion. Remember, we're not all living in one data center anymore. We have service discovery. So again, maybe DNS would have been sufficient before, but now we have systems that are spread geographically. We have to deal with multiple environments. We want to do advanced things like canary releases. Suddenly DNS isn't sufficient anymore. We have access control, so who can actually call this message? Who is it for? We then have concerns around per request routing. So do we want to apply any overrides there? Do we want to, chaos engineering, so inject faults? Or do we want to shadow traffic? A lot of concerns before that, when we start digging into traffic management, there's quite a bit there. And observability, so a characteristic of our systems to see how well we can understand its operation and production. And we want to know things like success rates, latency logs. So again, remember, we're looking to do latency-aware load balancing, request volumes. And that's just individual requests. At the same time, we might want to paint a picture of a business transaction that spans multiple systems. So you might have heard of open tracing and Zipkin. These are all things as well where we want to get the health of a business flow throughout our myriad services. And then reliability, our good old friends, the health checks. Circuit breakers as defined by Michael Nygaard in his book Release It. So again, to prevent cascading failure across your network. Retry policies. So again, in this love letter, if I get a return to sender, is it safe to send it again? Because we're all building idempotent services, right? Timeouts, our good old friend in distributed systems. So how do we make sure that our timeouts are generous enough such that valid traffic doesn't get rejected, but at the same time tight enough so you're not risking resource consumption and again causing reliability issues across the network. So when I first started reading through these, I thought, wow, this distributed computing thing is a lot harder than we thought. But well, there's a will, there's a way. And how do we make long distance relationships work? So with flow control, what happened is this went away from being the domain of the application developer, and rather we've pushed that down into the network layer. So no longer is our business logic cluttered with these reliability concerns, but now we can just, again, we take this for granted today. We call this TCP. Like, we're standing on the shoulders of giants. And Dylan Beatty mentioned it through the keynote as well and stole my thunder, which was a bit unfortunate. But this is absolutely amazing, because what that lets us do is all of this concern about traffic routing, it just happens. It's guaranteed delivery. It's in order. You get acknowledgements and resends from there, but we don't have to worry about it. And again, look at TCP and how it plays into that network layer. So again, at the physical layer, we're just dealing with raw bytes going across the wire. So at the data link layer, it's then reliable communication or transmission of packets, data frames between two computers. At the IP level, we have IPv4 and IPv6. This is how we do routing, so addressing. So when you put it in, how do I actually know where the traffic's going to get sent? Then at layer 4, we have transport. So this is, again, where TCP lives. This is the guaranteed delivery. Moving up, we have sessions. So again, rather, you can say TLS lives there. You can possibly say it lives across a number of other layers as well. This is also where WebSockets would live. So there's nothing magical about WebSockets. They're just TCP running within a browser security context. And then up here, up at layer 7, this is where we do the vast amount of our program. We just say HTTP client.send. And it happens magically. But there's all this engineering that happens under the hood. And this is just one example of how we solved it for flow control. But history has a habit of repeating itself. And again, the systems that we're building today are a lot more complicated. But even with these advanced capabilities that we need to support these systems, what we again want to do is abstract them away from the application developers themselves so we could focus on business logic. And this is where we came up with this stellar idea of an enterprise service bus. And these were actually a great idea at the time. So again, we can have all these different services. Some of them could be AMQP, some of them could be SOAP, maybe some form of JSON over HTTP. One might even be a REST service, who knows? And then each of these services would have an adapter. And then what we could do is we would then have reliable delivery and any transformations of business logic applied in the enterprise service bus. And this actually seems like a great model. So again, we have all this interconnection between our services. But again, there's always trade-offs. So at one of the companies I worked for in London, I was part of an integration team, and we were rock stars. First 50 integrations, we were smashing them out. We had all these different services, and we were absolutely amazing at it. And so when we were finished congratulating ourselves, there was something we looked at, it was like, we're up to a couple of hundred of these integrations. And then we started slowing down. So in typical sort of like Fred Brooks methodology, we just threw more people in the team, and suddenly we were a team of 10. So that made Friday night drinks absolutely lots of fun, but again, not from actually getting through the work, right? Because the trade-offs with this is an enterprise service bus, first of all, is a single point of failure. So you're going to have one of them. And this is not only from an infrastructure point of view, but also from a delivery centralized team. So again, we formed the constraint on our company's ability to deliver. So they could only deliver as quick as our team could move. So again, a single point of failure, both from an operational, but also an architecture perspective. And the reason why we slowed down is because we couldn't keep the mental model of all these different integrations, and we couldn't keep them separated. So again, regression testing became a massive overhead for us. And in the end, it actually had the opposite effect. So we put it in to be able to move faster. But fast forward a couple of years, and it was actually the very thing that was holding us back. And so then after a number of years looking at this, we as an industry said there has to be a different way of doing it. There has to be some alternatives. Then a lot of thinking around cloud native came up, and cloud native was really the confluence of a number of techniques and technologies. So first of all, we have DevOps, and at its core, DevOps is about continuous learning, improvement. And to be able to have fast feedback loops and be able to take an empirical approach to delivery, we also have continuous delivery then. So again, practice is about being able to do that safely and fast. And rather than making gut feel decisions, we can actually put something out based on data and move from there. But of course, at that time, we would have still been dealing with VMs. So again, very costly, slow to move, cumbersome. So again, on the other side, we then had, first of all, microservices. So how can we actually have small, discrete pieces of business functionality and business behavior, which can then change at their own pace? Or so the sales pitch goes. And then we have containers themselves. So again, this is actually a really nice package, because then I can have a very small service with a very small packaging format. And I have an absolutely amazing developer experience all the way from local through to production. And there's some people in the room that are probably thinking now, what happened service A and service B? Did they make it? I'm glad to say they did, and they had microservice babies. They're everywhere. But just like babies, this picture is a little bit messy, right? So previous we had service A and service B and one nice little line between the two. This is madness. There's integrations happening absolutely everywhere. And it's really complicated, right? And this is something I'm not sure as an industry we really expected, but the operability of microservice architectures is quite high in terms of the challenge they represent. So one of the key things, though, when I say service, is a service is business logic plus data. With the ESB model, a lot of the business logic actually left the services themselves and actually went into the central platform as well. So when I talk about an API is an entry point into a service. But with the service themselves, you want to have the data and the business logic close together, live together, because it should change together. And this is where the movement about Gorilla SOA really came from. So instead of having all this logic within the central enterprise service bus, it then said the logic should sit with the endpoints, the services themselves, and the pipes in between them should be dumb. Like, that's a really key point from there. So again, getting the logic back into the services where they should be. But once we've done that, a lot of the great value that we had from the enterprise service bus before in terms of like discovery, routing, circuit breakers as well, that's suddenly, again, just like back in the 1950s, it became the remit of the application developer again. So again, while we just want to be able to focus on business logic, we then now have to take advice of service discovery. So again, how do I route my messages to all of the different clients? So client-side load balancing as well. So circuit breakers, again, how do I prevent cascading failures? So if I have a downstream service and it hasn't responded successfully a number of times, why am I still sending traffic to it? Can I then provide a fallback to my own consumers? But one of the things from there is we often had this phrase like purported about microservices is that you can write them in whatever language you want. And again, so write the language that suits the particular problem. But service discovery, circuit breakers, like they're actually very complicated things. And in fact, there's libraries available for most of them. So in the Java space or the JVM, you might have heard of Hystrix from Netflix. So again, these are very complicated, or Poly in the .NET space. So you don't want to be writing these yourself. But then suddenly, if I want to write my new microservice in Julia or whatever, and it goes, oh, but someone hasn't written a circuit breaker library for me. Can I now use it? So a lot of these things as well is your ability to choose a language is often constrained by the libraries that are actually available for it. So again, it's this whole thing of standing on giants' shoulders. And what this actually leads a lot to, if you look at companies like Netflix, again, they say that you can, again, to their teams, you can write your languages, your services in whatever language you choose. But if you write them in Java, you will get all of this amazing help. If you write them in a different language, which you're absolutely free to do, you'll have to write that all yourself. Guess what happens? So a couple of years ago, I was over at Velocity in Santa Clara at an absolutely amazing conference. And the Netflix engineer that I spoke to, he described it as getting in the trough, that everyone just gets in the trough. So while they still had a microservice architecture, they definitely didn't have the freedom that is often touted around microservices. But again, what can we do to overcome this? So before, if we had all of this concern being with the application services themselves, then what we said, what we could do is every service could have its own dedicated sidecar proxy, which could run across process. So an example of this is Netflix Prada. And again, all of these languages, again, so if I want to take advantage of the Netflix OSS stack, but I don't want to write services that run on the JVM, I can have this run on the JVM, and I can get advantage of all of those within that sidecar proxy. And between the services, you're just talking language agnostic protocols, so HTTP. And because they're actually, again, deployed to the same host, we know that that connection is reliable between these two services. And then what we can do is all ingress and egress from those containers is via the sidecar proxy. So that's really nice. So again, we've encapsulated a lot of this logic as well. So another example of this is Airbnb Synapse, if you're looking for this as well. So this is quite a powerful pattern. And in fact, in many ways, this is the central idea or enabler for a service mesh as well. So this is what, a better microservices world could look like. So we absolutely still have the same interconnections between all of our services, but they all flow through a dedicated sidecar proxy now. And again, that handles a lot of the complicated business logic around reliable transmission of messages. And again, our services themselves can actually be focused on the business matters at hand. So onto the service mesh part itself. So this is a quote from William Morgan, who is the CEO of Buoyant. So Buoyant are a company who created Linkerd, one of the first commercially available service meshes. And he described it as this. So a service mesh is a dedicated infrastructure layer. So in the similar way, you can be thinking not the concern of the application developers themselves, but again, part of the underlying platform. And it's responsible for reliable delivery of messages. And it's typically implemented as a lightweight network proxies. So again, the sidecar proxies that we saw in the previous diagram. And the point as well at the end is without the application needing to be aware. So to paraphrase, you should not have to change your existing system to be able to take advantage of the service mesh. So from there, so long as you are talking in a language agnostic protocol, HTTP, and the traffic is routed through it, then you can take advantage of it. And that's one of the key principles. So a really important point now is a service mesh is not magic. It doesn't give us the ability to do things we could never, ever do in the industry before. But what it does allow us to do is shift where that responsibility lies. So that could be cross-process outside of the service itself, and then within that dedicated infrastructure layer comprising the service mesh. And the service mesh comprises two main parts. First of all, it has a data plane and a control plane. So the data plane is the path that the traffic takes. So the traffic that flows out of your particular service through its proxy and into the next proxy, anything that's on the path of the traffic flow between two services. But there's also a control plane, which we haven't looked at or hasn't appeared in one of the diagrams to date. And it sits out of band with the rest of the service mesh. But what it allows us to do is, instead of separate proxies that are completely isolated, we can then send instructions to the service mesh control plane, and it will then push that policy out to all of those sidecar proxies. So what we have is, again, one place that we can configure all of these services, but again, have those applied in each one of the sidecar proxies next to each service. And this is a massively powerful capability because just like with the ESB, it provides the same authoritative source of policies. So there's one place to configure this. There's one source of truth. But unlike an ESB, where the control plane and the data plane is one, if the control plane went down, that's absolutely fine. It's just that your sidecar proxies wouldn't receive policy updates for a period of time. But what we've done is we've taken the configuration off the critical path. So we no longer have that central or point of friction and possible failure. So I know what we're thinking now. We should sidecar everything, right? This is a great quote from Kelsey Hightower from Google. And it's really one of these things to say, focus on the basics first. So attaching sidecars to an application, there's no value in it until you're actually facing those problems as well. If there's a simple thing of just including that in one of your services first, start with this. When the operability of those services becomes sufficiently taxing on you, that's when you can start investing in techniques such as this. Okay, so far we've been talking rather abstractly about the pattern itself. So let's get a little bit more concrete. So we're going to talk about Istio, which is a service mesh from Google and a number of others in the consortium as well. And back in August, this had a really big milestone. So it released V1. So that's again after like a number of years of development. So absolutely huge milestone. And if anyone's wondering why there's a boat there, Istio is the Greek for sailing. So again, there's a bit of a link, just like Kubernetes is helmsman. So there seems to be a bit of a theme there. And Istio comprises a number of parts. So first of all, looking at the data plane. So Istio uses Envoy from Lyft as its sidecar proxy. So again, Envoy itself is a huge thing. There's actually a conference around it now as well, and Matt Klein blogs a lot about it as well. And it supports a huge raft of capabilities. And for intra-service communication, or inter-service communication, we have HTTP 1.1, we have HTTP 2, you could have gRPC, or really any derivative, or like if you have Thrift over TCP as well. So it gives you a huge amount of flexibility. And also you can have mutual TLS between them if you want as well. Istio splits the control plane into 3 main parts, each with a separate remit or responsibility. So first of all, we have pilot. So this is what you would have seen in the previous examples as well, of this is what we actually use to push config out to each one of our sidecars. We then have mixer. So mixer gathers telemetry from each one of those services as well to actually fuel some of our observability concerns, so success rates, latency. So again, this is where we also do policy checks to make sure that the correct version is applied to each one of these services as well. And then we also have Citadel. So you can think of Citadel as the certificate authority within Istio. So again, if you have mutual TLS between your services, it will be responsible for issuing those certificates. Okay, so right now, let's take a really quick look at Istio in action. And our example domain is pretty basic. So first of all, we would have seen with service A calling service B. But then as part of the demos which we'll go through, we'll look at releasing multiple versions of service C. So we have version 1, we have version 2, which has just gone into production, and we have this version 3 that we're working on. And throughout the course of this talk, we'll hope that we'll get it to prod, right? And then we also have service D as well, which is called by V2 of service. So again, this is the sort of model. For each one of the examples, we'll dig into a bit more about what we're looking to achieve, and then I'll show you it in action as well. But first of all, what we'll do is we'll take a real quick look in Kubernetes for this particular application as well. So for each one of the pods that we have in Kubernetes, we have, again, one for each one of these services. And what you'll notice as well is that each of them say ready 2 of 2. So that means there's 2 containers within each pod. So again, no prizes for guessing that one of them will be the service itself, and the other one will be the Istio proxy. So we can see from these is that each one of them will have the Istio proxy, which will handle the ingress and egress of traffic from those services as well. So what we'll do here is we'll just send a really quick amount of traffic to go through so you can just see a little bit of what we can do to update the policies. So from here, if anyone's familiar with the curl alias within PowerShell, I've actually removed this. So this is just like raw curl, just a bit of PowerShell going across the top then. And what we'll do here is just start an infinite loop where we can send traffic. And what we should see here is... Oh, my goodness, that's a... Right. So what we can see here is all of the traffic just being echoed back from version 1 of that service. So what we can do here now is update this traffic to now send it to V2. And what we'll see in this demo is that without releasing that service or deploying that service again, we now see that all the traffic is being routed to V2. And while you might say, Rob, that's a pretty basic example, but what we should be seeing already is that could be a canary release. So right now, I just did it as a 100% traffic swap. But you could say, send 2% of traffic to that, then send 5% of traffic to that. So you can change all of these policies dynamically without having to redeploy your services. But again, like I said, tech is cool in and of itself, but what's really exciting about it is the things that it now enables us to do. And testing in production got a bit of a bad rap for a while. So what I'm talking about here is not I only test in production. But again, it's a reflection of the types of systems that we're building now. So in traditional testing, we might have our particular system running in a test environment, which mightn't be representative of production. Okay, fine. With a certain set of data, at a certain time, with a certain configuration, and yet we think that gives us confidence to be able to push it into production and it won't fail. It massively highlights false confidence. The cause and effect between something happening in our system and actually being able to trace that back, that's just not feasible anymore. So we're dealing with the scenarios of unknown unknowns now, and this is really the shift from being able to focus on robustness insofar as how do we handle and avoid errors in our systems to resilience, so unplanned. How can our systems, when faced with an error, respond in a positive manner? So again, testing in production, absolutely a great idea, but the trick is doing it safely. So luckily over the last year, there's been a lot of great material that's been released about this. So this is a picture from Cindy Sridharan from Facebook. And she's documented testing in production having a number of discrete phases. So at deploy time, at release time, and then post-release when we actually have a product running. So for the purposes of this talk, I'm going to make a very clear distinction between a deployed service and a released service. A service is released once it's receiving any production traffic. Prior to that, it's just deployed. And again, at each one of these phases, we can apply a certain set of techniques. So we can do integration tests, pretty classic. We can do load tests. We can also do traffic shadowing. So again, we'll look at that in the demo in a second as well. Once we're actually receiving production traffic, we can do things like canary releases. We can do monitoring. We can do traffic shaping. We can also do pilot releases to a subset of users as well through feature flags. And then once we have in production as well, then we're into the space of how do we do sampling? How do we do tracing? Again, how do we actually minimize the cost of ownership of our systems while maximizing the value we get from it? Okay, so traffic mirroring. So what we're looking from here is often with the test environments that we have, even if we can get the environments right, often the data is the tricky part. Do you grab your production data? Do you try to de-identify it? Or do you just create this sort of like sample set of data as well? And again, the level to which it reflects production, again, anyone's guess, could change over time. So imagine if we could do this. Bear with me a second. Imagine if you could grab a production traffic load, deploy your new service, and then just magically copy all of that traffic and send it to your new service. And that's what we can do with traffic mirroring. So again, in this particular case, we can have V1 released and all the traffic going there. And then out of band, we can copy all of that traffic and send it to V2. But the trick here is it's sent out of band. So again, even if this fails horribly, the user won't be affected or even aware that it's happening. And what this will also do is then append on a -shadow suffix to the host and authority meta header in HTTP. So again, that service can actually identify that this is shadowed traffic. So again, if there was going to be a mutation that would happen later on in the process, it could then say, don't apply it. Or again, idempotent services, again, you can apply that with retry policies as well. Okay, so let's take a look at what that would look like. Okay, so to do this, we're going to actually trail the logs of each of these services. So first of all, what we do from here is, again, with kubectl is select that and then just look at the logs for each of these. So we have V1 at the top, and then we have V2 below. So first of all, what I'm going to do is just make sure that I'm just sending traffic to V1. And then as I'm sending traffic, again, you can just see all of it V1. And you can see that the logs across the top will be ticky along, but we won't see anything then coming through. OK, so what we'll actually do here is is I'll just update the host header just so you can see it refresh. So we'll say, so again, v1 is updating, nothing going to v2 as yet. But again, with this policy, what we can do now is update all that traffic to be mirrored from v1 to v2. And now suddenly what you see is all of this traffic being copied across, but the dash shadow being suffixed to the end as well. And this is all still deployed. We haven't released this yet. So even though it's representative of production traffic, it is actually shadowed. So none of our users would actually be affected, even if service 2 fell down to the heap. And again, with canary releases. So this is where we actually want to send production traffic to it. So we've mirrored our traffic. We've got a lot of confidence that, yep, this looks good. They'll press the button. But again, from a risk-adverse perspective, we might still say, well, something might happen. So let's say you could either do it to a pilot group of users or, again, just a percentage of traffic. So we've already seen this. Whereas we did a straight 100% swap, you could easily do 5% or 95%. I actually don't think we are too far away from like a rolling update policy where we could say, apply it started at 2%, keep ratcheting it up every 5 or 10 minutes. When you reach 100%, nuke the old service and away we go. Like that would absolutely be incredible. If you come up with any errors, then that's fine. Just reroute to the original policy as well. Okay, so circuit breakers are table stakes for distributed systems. So any outbound call from your system to another cross-process, wrap it in a circuit breaker. Otherwise, you're potentially making matters worse for that downstream service. If it's still struggling to cater for the amount of load and you just keep sending traffic to it, then that's just likely making matters worse. But at the same time, it's responding slowly, then you could do your users a favor by saying, no, I'm just not comfortable with how that's performing, so I'm going to return a canned value, or even a more timely error back is preferable as well. So what we'll look to do here is we've now released v2, and we can look in our demo that we'll just route traffic 50-50 between those two services. But then we'll introduce service C, and service C then will throw errors. But at the same time, in this example, it's deterministic. I literally have a throw if you look at the code. It always fails. But in real life, that could be for any number of reasons. Maybe part of the infrastructure, or a firewall rule got changed, any one of those policies. But it suddenly starts throwing errors. But what we'd like to be able to do with that then is prevent that error from permeating the rest of our system as well and restore good service as quickly as possible. So let's take a quick example of that. So again, we can just send traffic across. So in this case now, what I'm going to do is, first of all, just send it to the live version. So this will just do 50-50 load balancing between version 1 and version 2. And then what we're going to do is we're going to include service C, and boom! We're suddenly seeing errors coming back as well. But again, if this is happening in the middle of the night, then is someone going to be on call to fix this? What we'd like is the system to be able to identify this and then remove the erroneous nodes from that availability pool. So in Istio nomenclature, it's an outlier detection. So what we'll see here is when we press this, I've set up the rule to accept 5 requests, so it's going to be 5 consecutive errors. And in that case, it's going to be removed from the pool for a period of 20 seconds. So you'll see those errors just going through there. And now it's back to v1 and v2. So in a couple of seconds, what you'll see is another 5 errors come through on this console. And what we're doing there is it's actually going to recheck, first of all, after 20 seconds. And then it's going to do an exponential back off. So it's going to be a product of that time by the number of times it's been removed from the pool. So that way, again, even if it's a transient or intermittent error, we'll remove it initially and then check later on. But at the same time, we're just going to do more and more conservative checks after that. And again, what we can do is just update the policy again to just be, let's just say, live versions. And any of the exclusions then would be removed. So again, if you update the policy, you can just bring it straight back in if you wanted to again afterwards. But again, I haven't had to do anything from here. And again, I can have all those circuit breakers across all of my services, timeout for all of my services, applied via this policy and have it pushed up to all of those services without having to deploy them. OK, so this is a bit that really excites me. And I think it's going to be an area that we're seeing a lot more over the next year. So if you want to speak at a conference, I think this will be a massively topical subject. So what we're really doing here, though, is accepting that, again, we don't know it all. It's non-deterministic in terms of how our systems will fail in production. So you can think of chaos engineering or chaos testing as exploratory testing of the non-functional characteristics of your systems, such that if those characteristics fail, your system is no longer functional. Right? So, but what we're actually doing here is doing experiments. So to say, in production, let's actually generate faults. So I could inject errors into my system and see how it behaves. So if anyone's, again, read over the years about Chaos Monkey or Simian Army, that's the very same idea. So can I take a node out of this availability pool and still have the service remain up to, can I nuke an entire data center and have the quality of my service remain up? What we're doing here, though, is doing it at application level. So in this particular example, we have service A will call A and B, and then C calls down to service D as well. But we're going to run an experiment. We're going to say, if I inject 25% of errors on that downstream leg from C to B, how will the system respond? Like, do we have any policy in place that will compensate for those errors? So what we're going to do here is roll that policy, and you'll see now each one of those legs we're sort of seeing slightly intermittent, so every so 8 or so. So that's 25% of 50. But what we'll see here is we'll take a quick look at Grafana as well, and this actually comes free with, basically out of the box with Istio as well. So all of that instrumentation instantly gets sent from each one of those policies, gathered back up into Mixer, and then displayed on this dashboard. So what we can see now is pretty much that we have, again, 92% of our requests are passing. But again, our system isn't compensating for that injected fault. So what could we do about that? So what we could do here is, wouldn't it be really nice if service C, again, because that call down to D is idempotent, to just retry it again. And if it fails, maybe for an intermittent error, just retry that again. So in this particular case, what we'll do here is, again, still with injecting the fault, we'll do a retry policy. So that will be, if service C detects that the downstream call has failed, it's going to try up to 3 more times. And what we do in the retry policy as well is we've also reduced the timeout for that as well. So instead of the default 15 seconds, which you get out of the box, I've just said it's going to be 2 seconds. So again, we're just being a bit more conservative to say, well, if that call fails, try it a few more times, but after that, you can then have potentially the circuit breaker kick in as well if we can compensate through a retry policy. And what we can now see is, even though we're still injecting the faults, we're actually retrying those calls. So again, we'll see this chart go back up to 100% from here. And I wouldn't keep injecting those faults, but run these as experiments across your system. And another really nice thing that we could do from here is, because Istio knows all of the traffic that's flowing between all of my services, you can get things like architecture diagrams for free. So why generate these yourself? If we know the shape of all the traffic that flows through it, we can then see what's the actual shape of my system and then start drilling in. So this is just one potential visualization, but you could do .graph or any other formats as well, a number of them. So again, you can put it into your graphing tool of choice. But with these systems that change so rapidly, trying to create an accurate architecture diagram to any level of fidelity is an exercise in futility. We can have these generated for us now. And the other thing is, right, so far as I've been doing everything with policies, so it's been applied to everything. But what I could do as well is apply specific instructions to a single request. So we can send HTTP headers, as documented on the Envoy side, that will then allow me to overwrite those policies for a particular request. So you might be able to say, for this particular user, actually see what would happen if I reduced the timeout to 1 second instead of 15 seconds. But you didn't want to do it as a policy across, across all of your services as well. So a key point here is service meshes enable us to decouple traffic management from infrastructure scaling. So Kubernetes gives us absolutely amazing abstractions at the infrastructure layer. So if Docker abstracts us from the operating system, Kubernetes abstracts us from the entire infrastructure layer. I can take one workload in one cloud provider and run it on another cloud provider. Kubernetes gives us nothing at layer 7. And that's a lot of the concerns that we as application developers have. And this is where service meshes play. So this is about application level value on top of those at the infrastructure layer that, first of all, containerization and then Kubernetes gave itself. But we have them as separate concerns, and we can treat them correctly as separate considerations. OK, so service meshes as part of an infrastructure layer or conceptual infrastructure layer are typically supported by a platform team within an enterprise. So again, making sure that the service itself is robust, resilient. So pop quiz. Given it's going to be supported by service developers, do application developers even need to be aware that the service mesh exists? Who thinks yes? Who thinks no? It's always a trick question. So again, Jay Krebs had a quote I really like about microservices back in 2014. And I don't know if anyone else has experience with distributed objects, but again, there was this great idea back in the J2EE space where we could have these objects, and I call a method on them. And that method might actually result in a network call or just to another object from there. So we completely abstracted that away. No surprise, that was an absolute disaster because you couldn't have any empathy about how costly an operation would be. You just didn't know what would happen. So at the same time from here is while the service itself will be supported by a centralized team with dedicated expertise, service developers should be aware of the configuration for your services as well. So you will still own the configuration of your services, just not the platform on which it runs as well. So the question now is, God, these service meshes are amazing. How do I get started? Slowly. So again, another quote from William Morgan. And he's basically saying that there's a lot of hype around service meshes today. Some of it may be well-founded. Other might just be hyperbole and we'll have a dashed broken dreams in a year's time. But what he's really saying is don't start with a service mesh. If you're starting a new Greenfields project, you probably don't want to reach for a service mesh straight off the bat. Get users, make them happy, deliver value. If then your services are representing quite a high cost of ownership, or you're spending a lot of time just trying to understand how they operate, that's where a service mesh plays really nicely. And there is a bit of a shift in the industry around this. So Linkerd was notoriously difficult to configure. There was a huge raft of values, and you could apply it. It was quite daunting when you looked at the configuration file. If you look at what Boyd have done with Conduit, more recently renamed to Linkerd 2, it takes a far leaner approach. and allows only like a couple of values to be set at a time, but again, gradual adoption. So my advice there would be start with a single capability. Don't try to have it do everything on day one. Instrumentation's a good one because it generally runs out of band. So do that. Have your services send telemetry. Have it displayed on your dashboards. Start generating some of the architecture diagrams from the content as well. And then once you've understood how to operate that and you've grown some capability or experience in that area, then move on to the next capability, and so on and so forth. Okay, so takeaways. A service mesh is a dedicated infrastructure layer, making service-to-service communication safe. And when I say service-to-service communication, I'm talking about RPC. And RPC is part of a far wider integration challenge. It's not a solution for everything, but it is a very important piece of the puzzle. If your microservices are representing a challenge to operate and the cost of ownership is high, and you're spending too much time on trying to make just run and not on build, then again, a service mesh can help with some of that friction. And service meshes afford gradual adoption. You can start with a small piece, then proceed on to the next one, and so on and so forth. Take advantage of this. It's an incredibly powerful capability. Okay, we have about 6 minutes for questions.
Is it possible to use service mesh and the traditional microservices in a mixed environment and then gradually move rather than just, I mean, you have some services working on mesh and fully isolated from microservices. So instead of, is it clear or should I explain that?
So the question is, I'll just repeat it back and hopefully that I got the right sense. So again, with microservices, is it still okay to have some of the services which are running on the mesh or running on, let's just say, Kubernetes with Istio sidecars injected across to other services in your fleet which don't have that access? Yeah, absolutely. So one of the parts with service meshes is you can still put in like a service entry which will be egress from the mesh. So you can still absolutely interface with things outside of like that mesh as well. And yeah, that's very typical.
So it won't affect anything like service resolution, something like that, so service discovery.
Yeah, so again, that's actually logic that you build into that service entry point as well, where you're going to say, internally, we're going to resolve it to this, but then externally, that will then be the DNS entry outside of the mesh from there. But yeah, particularly the feature you're looking for is called service entry, as opposed to virtual services, which we do to configure for each one of the policies for those particular services. Hi.
Hi. In the time you did traffic shadowing for deploying your service, it didn't mention anything about if you have a database behind your service and they're sharing database. I assume they're same service, different versions. And do you need to isolate or abstract your database layering, avoid having impact twice?
Great question. So what you would have, so the question was, with traffic shadowing, if you have a new version of the service, but it shares a persistent store, do you then have to compensate for potentially that action being applied twice? So for instance, if you're doing an event sourcing model, you wouldn't want the same event to be persisted in your log twice. What you would have noticed as well is that the shadow traffic had -shadow suffix on each one of those requests as well. So in that particular logic, you would then see in your app to say, this is shadowed traffic. Don't actually write to the database from there. Yeah.
But that would mean that we are coupling it back into applications.
There's always going to be slight trade-offs in terms of traffic shadowing. So you're correct. You have to be aware not of the mesh, but the fact that your traffic is being shadowed. So we have time for one more question. Hi.
Is this Istio, is this new, came through recently, you said? What stage is it at to get into production? And are there others?
So the question is, how new is Istio? Is it safe to use in production, and what alternatives would you have in the market? So Istio reached V1 back in August, and it has a number of huge backers behind it, including Google. So that's quite a mature offering. We also have Linkerd, which has been released for about 18 months now, I believe. So that's incredibly battle tested and mature. So it actually runs on the JVM. And typically a deployment for that would be a little bit different. Because it runs on the JVM, it's actually quite heavy. So what we would do with that is typically not have sidecars injected into each one of the pods, but rather we'd run them as a daemon set so with each host, but we would still have ingress and egress through that daemon host through to the other services. But particularly from there, so Linkerd is another option, and we also have Linkerd 2 as well now. So that's probably your main ones. Okay, so I think we're out of time. Thank you so much for coming to this talk. I really hope you enjoyed it.